Let's build a Wavetable synthesizer plugin in the JUCE C++ framework. Hi everyone, this is Jan Wilczek from the WolfSound.com, and in this video we are going to use the JUCE C++ framework to implement a VST3 plugin with a Wavetable synthesizer that can be used in any digital audio workstation that you want to. If you don't know what Wavetable synthesis is, I highly encourage you to check out one of my previous videos. Also, if you would like to know how to implement Wavetable synthesis in Python, I've also got a video on that. In this video, we are focusing solely on a plugin in C++. For this, you need to have the JUCE framework installed and an IDE for C++ of your choice. I am using JUCE version 6.0.5. If you're ready, let's get started. The JUCE C++ framework is a framework for building audio-related applications. We want to use it because it easily connects our platform, so in this case a PC running a digital audio workstation, with our audio processing code, and it generates all these plugin bindings which we don't have to go into, and it makes writing audio-related code so much easier. In JUCE, there are two main classes that are generated for you that you are expected to fill. One is called the plugin editor, and it is the graphical user interface that has all the knobs, all the controls that you'd like to regulate. In this video, we're not dealing with the plugin editor because our Wavetable synthesizer won't need any graphical user interface. But the other component, the plugin processor, is something that deals solely with audio processing. And in the plugin processor, we'll insert our audio processing code related to the synthesizer. To create a project in JUCE, you need to launch what is called a producer. Here you go to New Project, and then you need to be careful here. So it's like plugin basic, that's what we want to do. And here's a tricky part. Here is the name of your project, and it's not very well visible. So you may end up with classes called New Project Plugin Processor. But no, we want to build a Wavetable synthesizer. So we'll write this, WavetableSynth. Okay, I have my WavetableSynth tutorial project name specified. Now we need to export this project for a specific IDE. And I am using Visual Studio 2019, but you may pick any other IDE that you would like. Okay, now we click Create Project. And we choose the folder where our project files should be located in. So JUCE will create a folder with the name of the project that we specified. Okay, and we have our project. So here we may explore already the generated source files. But before we go into that, I just want to go over here to the settings. And here I want to specify that we are building a synthesizer. So I'll put here company name, which is of course WolfSound, and then company website, where you will find the full article containing the comments to this code, and also more materials on audio processing and sound synthesis. Now we go here, specify that we want to output the VST3 plugin, because that's the one that will run on my computer. Then we specify plugin is a synth because, well, it is a synth. Then we need the MIDI input because we need to somehow know how we play this synthesizer. Also, we want to specify MIDI output so that we don't discard the MIDI information that is contained in our MIDI buffer. Okay, plugin name, plugin description. Okay. Actually, we don't need to do anything else. Now we just click here, generate, and it will automatically open the IDE of our choice. And let's see what JUCE has prepared for us. We can see two projects here, and shared code is something that is the core of our processing. So our shared code will be used for all other projects or exports that we want to have. As we can see, we export our plugin only to the VST3 format. So our shared code will be compiled to, let's say, output agnostic library type, and then this library will be used by the interface projects such as this one, VST3. So we don't need to deal with anything that's here. We only deal with what is in the shared code, and in the shared code we have our plugin editor, and we also have the plugin processor. And you can see that our plugin processor is called WavetableSynth Tutorial Audio Processor. So exactly how we called our project plus the audio processor suffix. Now we won't deal with plugin editor, we'll only deal with plugin processor. But before we do any code changes, let us just build our project and see if it compiles just fine. Okay, it compiled. We can now make new changes to it and implement our Wavetable synthesizer. To start coding our Wavetable synthesizer, we'll create the WavetableSynth class. We won't create a constructor because we want our class to be default constructed, but what we need is a public interface to two member functions. In JUCE, before the actual processing or at any major settings change, there is a function which is called to prepareToPlay. And in this prepareToPlay, we'll let our synthesizer know what is the sampling rate. We also can specify what's the size of the audio block we're processing, but we don't need that right now. So we'll write here the public interface. I'll be prepareToPlay, and we want to pass here the sample rate. And the second thing we want to do is we want to have a method which is called processBlock. And this is the other member function that we need to implement. And here be our actual processing. Let's look at just how this member function looks. Okay, here it is. As we can see, it's processBlock, and it takes an audio buffer and a MIDI buffer. And we want to exactly copy that signature so that we know that we have it correctly implemented. And for simplicity, I'll just import the JUCE header. Okay, now that we have our two member functions, we are ready to implement them. For this, we need to have here the private part, which is the sample rate that we store. And some other elements will come in handy later. Now, we can add a Wavetable synthesizer to our plugin processor. So here, we'll have WavetableSynth member. And for this, we of course need to include the relevant header file, which appears here. Now, we don't need the plugin processor anymore in the header. We can write our processing code, and we'll only fill these two functions that I talked about. So here, let's go to prepareToPlay, okay. And here we'll just call synth prepareToPlay sample rate. And as we don't need the other parameter, we can remove it here so that we don't get a warning that we didn't use it in this function. Now, the other function that we need to implement is processBlock. And here's some code that we'll just delete. And here's our audio buffer. And this audio buffer stores the samples that we get. Then we do something with this buffer, what we want, and then we output this buffer. And these are the samples that we play out from our plugin. And the MIDI buffer stores the MIDI messages that happened during that audio buffer block. And we'll need both of these for our processing, because the MIDI buffer will store the information on the notes or the keys that were pressed. But before we do that, we need to clear our buffer of any samples that it already has. Why? Because there is a possibility that the buffer contains some garbage. And these garbage samples are dangerous because they can damage our audio output. And in JUCE, we can simply clear the buffer by calling buffer.clear. And that's all we need to do. Now we pass this to our synthesizer. And that's all the code that we need to write inside the code generated by JUCE. Now everything else here will be written by us. So let's implement these member functions such as prepareToPlay and processBlock. Here we just store the sample rate that the plugin processor has given us. And for the processBlock, we want to do the following. We have our block of samples, and at some points there may have happened MIDI messages. So what we want to do is we want to read out these MIDI messages and render the sound in between these MIDI messages. Because in between, no synthesizer parameters were changed. So the environment stays constant and our sound can get generated. So as you see, we're doing here this kind of the top-down approach. And this code that we're writing right now is kind of general to every synthesizer that you will write with JUCE. So let's start with the sample that we want to mark as a start of our processing block. Obviously we want to start with 0. And now what we do is we iterate over the MIDI buffer. And MIDI messages contains actually instances of class MIDI metadata. And to get the actual message, we need to call the getMessage member function. Now we want to know when this MIDI event happened. And for this, we need again an index of the sample at which this event happened. We write this using the method or the member function getTimestamp. And as you can see, this timestamp is in the double format, and it's not something that we want. We want to have it in the int format. From the JUCE documentation, you can learn in this context, this index is definitely an int. So here we can safely cast it to an int. Having it in the int format will allow us to use it in the iteration process. We are starting from sample 0, and then somewhere happened a MIDI event. So we want to render anything between the sample, current sample, and that MIDI event. So we call render buffer current sample and MIDI event sample. So there's not a member function that does this functionality, but we'll implement it soon. It should render, so generate all our sound in the specified interval. So from current sample to MIDI event sample, but excluding the MIDI event sample, because we're using, again, this standard template library style of ranges. Now, after rendering the sound, we can handle this MIDI event. And this member function will analyze what happened in the MIDI messages and, for example, will initiate playing some note. And afterwards, we can update our current sample to be at the index of the MIDI event. And after all MIDI events have been handled, we still need to render the last portion of the audio buffer. So again, we call render current sample, but now we want to process till the end of the block. Okay, and this is our synthesizer. Now let's write the handleMIDI member function. So we add handleMidiEvent to the interface of WavetableSynth, and we pass it the const reference to the MIDI message. And now we can implement this. Okay, and how does this type of implementation may look like? The MIDI event is either a key was pressed or a key was released, or there was some other type of control information. We'll only here handle very basic type of MIDI note on event and MIDI note off event. And for this, we just need to check what is the type of the MIDI event that we passed in. So if it is a note on event, so some note was pressed, we can handle this somehow. If it was a note off event, we again can handle it. We can stop playing some note. And the last type that is interesting to us in this video is that the MIDI event of all notes off. So we received a message that all notes were stopped. To handle these events, what we need to have is a bunch of oscillators. And oscillators, in this case, are quite, let's say, low level at this point, because usually we have voices. And each voice may consist out of many oscillators. But here, for simplicity, we'll have as many oscillators as the keys on the piano keyboard. And each of these oscillators will be capable of playing exactly that key. Here we get the MIDI note number, and we'll call it oscillator ID. And we also will need to retrieve the frequency that we want to set to our oscillator. And then we'll pick an oscillator out of our oscillator set that we'll initialize with the computed frequency. Now this oscillator will start playing. Now let's implement MIDI note number to frequency because it's quite straightforward. So let me add this to the interface, and we can again make it private. It returns a float and it takes in an int. And the formula is quite straightforward. We want to tune our instrument to be 440 Hz at A4. So we may write A4 frequency, it stands for fundamental frequency, is 440 Hz. The MIDI note number for the A4 key on the MIDI keyboard is 69. Actually, what I can do, I can make these constant expressions. Finally, we may also write how many semitones there are in an octave. There are 12. We use floats because the final computation will be much easier this way. What do we return? We return the A4 frequency, the fundamental frequency, shifted relative to its position. We calculate everything with respect to this A4. For example, if our MIDI note number was 69, so exactly A4, then we should return 440. And we do this by subtracting exactly the MIDI note number. And this gives us the absolute difference between the MIDI note number and the A4 MIDI note number. But we want a relative change because the equal tempered scale is relative. That's why you have 2 to the power, and now comes the difference in semitones. And the difference in semitones is exactly the absolute difference divided by 12. And so we implemented our MIDI note number to frequency function. Now we might turn to how to have our oscillators in place, because we see that we have oscillators here, but we have not implemented them yet. So let's maybe do this now. What is a wavetable oscillator? As you may remember from the Python video, a wavetable oscillator is something that has a wavetable, and to generate sound, it loops over it. So let's define a wavetable oscillator. I again create a class. And what this class does is it holds a wavetable and a sampling rate to make the looping easy. As you can see, our wavetable is a vector of floats. Now we define the sampling rate, but as we know, there is also something different necessary, and that is the index and the index increment. And this may be readily initialized to 0. Now let's write the constructor where we pass in the wavetable and the sampling rate. And let us use the initializer list here. And that's everything we need to know for the constructor. Now, how will actual sound generation go? We need two functions here. First one that sets the frequency of this particular oscillator, and another function that actually loops over the wavetable, so the actual core of the wavetable synthesis algorithm. Let's first write the set frequency function, which calculates the index increment by which the index will be incremented at each iteration. And here we implement the formula from the wavetable synthesis algorithm theory video. We don't reset the index because we want to be able to continuously change the frequency. As we remember, the index increment is exactly frequency times the length of the wavetable divided by the sampling rate. Here we need to cast to the float. And sample rate is a double, so we need to cast it too. Now that we have the frequency set, we may implement looping over the wavetable. And we'll do this like this. We'll implement a function getSample, and getSample will return one sample of the oscillator and increment our index. The first thing we do is we retrieve the sample using linear interpolation, and for that we have a separate member function. It can be a member function because then it will have access to the wavetable, to the index, and to the wavetable size, which are necessary for the linear interpolation. When we got the sample, now we may increment the index, and now we may perform this fmod operation that I explained in the wavetable synthesis theory video. So just for a quick reminder, it will take our index and bring it back to the 0 to wavetable size range. And for this, we need the CMath header. And now we return the sample. You may wonder why we cannot increment the index and only then return the sample. If we did that, we would never start looping with index 0, because if we press a key, then the first returned value would have its index different from 0 because we already incremented it. So we do it just to always start with index equal to 0. And here we also need to cast the wavetable size to a float. Okay, we have our sample, but we still need to write the linear interpolation code. Let me just quickly write the appropriate weighting. I explained linear interpolation in the Python wavetable synthesis algorithm video and also in the wavetable synthesis theory video. But just for a quick reminder, if we have an index between two integer indices, then we return the weighted sum of the wavetable values that correspond to these nearest integer indices. But the weights that we take for these two values are the distances from the index to the other integer index. And in this way, we may weight the sample that the index is nearer to with a larger weight. To truncate the index, we just use the static cast to the integer because we know that index is a floating point number. Now the next index is truncated index plus 1 and again brought back to this range from 0 to wavetable size. I'm writing explicit casts here because I know that it may be problematic at runtime, and sometimes we get strange errors just because we didn't cast the numbers properly. Okay, now that we have these two indices, we may calculate the weights with which we weight them. And now we may return the interpolated sample. Oh, and here we made an error because here should be next index, not next index wait. Thank you, compiler. Okay, we've completed our linear interpolation code. And now our oscillator is already playing. But we need one more thing. We need to be able to stop it. And then we also need to be able to see whether it is actually playing so that we don't do anything strange. The stop member function will reset the index to 0 and the index increment also to 0. In this way, even if the getSampleMember function will be called, we'll be sure that it won't return anything meaningful. But it is also important that the calling code won't call getSample if the oscillator is stopped. The calling code should ideally ask the oscillator if it is playing. We can determine whether it is playing if its index increment is different from 0. Because if it's equal to 0, then there is no looping around the wavetable. Let me show you how it looks in code. Okay, and that's it for our wavetable oscillator. Now let's see how can we initialize enough oscillators so that we can play our wavetable synthesizer. For this we go to the WavetableSynth and we look at the function prepareToPlay. So here what we need to do is we need to initialize the oscillator. And we need to do that every time the sampling rate changes because the oscillators also depend on the sampling rate. In order to initialize oscillators, we need to contain them somehow. So I'll add a vector of wavetable oscillators that we can initialize. Here, let us set the number of oscillators that we want to have. And we set it to 128 because that is the number of the MIDI node numbers that we have available. And we choose to create 128 oscillators because we want to have a polyphonic wavetable synthesizer so that we can play multiple keys at once. So each oscillator will be assigned to its own unique key. To initialize the oscillators, we need to pass them the wavetable. So we need to generate the wavetable first. To generate a wavetable, we need the length of this wavetable, and let's fix it to be 64 samples. This number may be specified by the user, but I decided to fix it for simplicity. And now we need to loop over the wavetable length and assign each point a value of a sine function, and we want to have just one period of the sine stored. So we'll increase the argument of the sine that we'll call so std sine by the 2 pi divided by the length of the wavetable. And for this we need number pi. So pi is in general available through some headers, but let's for simplicity again define it as a constant. That's a way I found on Stack Overflow how to have the pi constant quickly in your C++ code. Now finally we may loop over our wavetable. And again, I write here these explicit casts just to be on the safe side. Okay, we have generated our wavetable. Now we may initialize our oscillators with it. Just to be sure that when we're initializing our oscillators, we will clear them first. Because if we change the sampling rate during processing, it may be so that we already had some oscillators. And then place back takes the arguments to the constructor of the Wavetable oscillator. So we have very nice code and we don't have unnecessary moves or copies here. Let's now return to our MIDI node number handling code. If a MIDI event is node on, we already know that we set the frequency of the appropriate oscillator. If it's node off, then we again need to stop this oscillator. And naturally, if we receive an all nodes off message, we need to iterate over all oscillators and stop every one of them. With this, our MIDI handling code is complete. The last thing we need to do is to write the render function. And render, as you remember, should generate samples from a specified beginning sample up to the specified end sample without including this sample. And we'll do this in the way that we iterate over oscillators, and only for the active ones we'll query the next sample in a specified range. And we'll add these samples just to one channel, and then we'll copy this channel over all other channels. For more specific applications you may of course change that, but for educational purposes we just want to copy our synthesizer's output over every output channel. Okay, so what do we do? First we get the pointer to the first channel. Now we iterate over our oscillators. We ask if they are active. And if they are, we ask them to give us samples in the specified range. Note that we add to the channel, because if we just assigned, each oscillator that is active would override what is already in the channel. So we cleared the buffer before, as you remember, and now we just add. So if there's no oscillator playing, it will be zeros, and each other oscillator that is playing will just add its values here. Now, you may also wonder whether we will not exceed the possible range of playing. Yes, and that is an issue, and you need specific strategies to deal with the loudness of the oscillator. So the sound shouldn't be significantly louder if we have multiple keys playing at once, and it also shouldn't be significantly silent if we just play one note. But that's, a topic for a whole different video. Okay, now that we've rendered to the first channel, we can now copy this to all remaining channels. Now, at the end, we rendered all our oscillators into the buffer. So we now are able to test our synthesizer. Okay, we've managed to build our project. Now let's launch it in the JUCE audio plugin host. Okay, so in the audio plugin host, and now what we need to do, we need to discover our plugin. So let's go to edit the list of available plugins and options and scan for new or updated plugins. And I already have the folder that contains possible plugins that I will create, but here you may add the folder that you created your project in. So in case you have your project in a folder that wasn't added here, you can edit here with the plus sign and then again click scan. Okay, and we see that we have our WavetableSynth tutorial here. Great! Okay, we have one MIDI input, one MIDI output, and 2 audio output channels. Now it's the great moment whether it will work or not. It works! Okay, this is the debug version of our synthesizer, but the release version would of course work much faster. One thing that you may observe here is that our Wavetable synthesizer has a click when we press a note or release one. And this is related to the lack of the fade in and the fade out after pressing the key. And this also could be a topic of another video, because we could already introduce the concept of amplitude envelope. If you want to make this work fast, then you just need to write a code that, takes the samples after pressing a key for, let's say, 1,000 samples from the minimum volume, so 0, to the maximum volume that you set. You may also hear some ringing here, but it's also related to the fact that all the oscillators produce samples in the -1 to 1 range. So we have really loud synthesizer. This plugin can be easily imported to a DAW of choice. You can also implement new wavetables to play, also a graphical user interface, because here we just have hello world, but it's a good starting point for any other synthesizer that you'll implement in the future. That's it for our Wavetable synthesizer plugin tutorial in JUCE. If you have any questions, don't hesitate to ask them in the comments below. If you want the full code, I have also put the link to the full article over at WolfSound.com that you can also find in the description, and there every piece of code is heavily commented, and there's also a related repository on GitHub when you can actually download all the code and run it yourself. Or if you had trouble following what I just presented, you can compare it to your code and see what may be missing, where the possible mistakes are. If you like the video, definitely give me a thumbs up, subscribe to the channel, and please let me know if these tutorials are helpful to you, because otherwise then what's the point of making them? Finally, a big shout out to Aalto Acoustics Lab for letting me use their equipment and also office space. If you are interested what they are doing, what they're involved with in acoustics and audio processing, I have also put the link to the Acoustics Lab in the description below. Other than that, I wish you a pleasant day and see you in the next video. Take care.